All right, guys. So we're just continuing. This is part two of our Unit One review, and we're still on just 1-2 here. So let's keep on going. So remember, PES is really just you're just talking about how electrons are attracted to the nucleus. And so remember, the more protons in the nucleus, the more attractive they are. But as you get more and more protons in the nucleus, you start to get more and more energy levels, and then you get shielding effect, right? And so, right, the radius of an atom or a radius of an ion is going to depend on the electron's attraction to the nucleus versus the electrons, especially in higher energy levels, being shielded, repelled by their core electrons. And so there's this, balancing act. So I might have more protons in the nucleus, but if I have more energy levels of electrons, I still might have a bigger radius, right? So if you remember, like radius decreases going left to right because as you go left to right, you're gaining protons in the nucleus, right? As I go left to right across the periodic table, I'm gaining protons in the nucleus, but I'm not gaining energy levels. So my radius gets smaller and smaller because the electrons are more and more and more attracted to the nucleus. But then as I go down, I gain an energy level, and now there's more shielding because now there's more core electrons because now I have a new valence shell, and so my radius gets bigger even though I have more protons, right? So just this balancing act between Coulombic attraction versus Coulombic repulsion, right? So remember snowman for the radius trend. But remember, the ionic trend is different. If you have ions, remember, a lot of times you're comparing things that are isoelectronic. That means the same electron configuration. So remember, if you have the same number of electrons, but a different number of protons, the one with more protons is going to be smaller, the one with less protons is going to be bigger, right? So like if we're talking about, right, so like nitrogen, the atom, neutral, is going to be smaller than aluminum atoms. But if we look at N3 minus versus aluminum 3 plus, they both have the same electron structure as neon, the same electron configuration as neon. They both have 10 electrons. So aluminum, because it has 13 protons in the nucleus, aluminum ions are going to be a lot smaller than N3 minus ions because N3 minus only has 7 protons in the nucleus. Aluminum 3 plus has 13 protons in the nucleus, right? So ions are a different story, right? So just, remember that part of the radius trend. For ionization energy, a couple things we want to remember. We want to remember the trend is just for first ionization energy. So as we go left to right across the periodic table, we get an increase in ionization energy. That's because our radius is getting smaller and smaller. The electrons are getting closer to the nucleus. The nucleus has a greater charge, so there's greater Coulombic attraction. So it's harder and harder to remove an electron, right? That's what ionization energy is, the amount of energy required to remove an electron, right? So the trend is just for first ionization, okay? But in that trend, remember there's a couple of exceptions. So notice magnesium to aluminum, it actually goes down, okay? And then phosphorus to sulfur, it actually goes down, even though, right, aluminum is further to the right than magnesium. So based on the trend, it should increase, but it actually dips down a little bit here. And then the same thing happens between phosphorus and sulfur. And if we went up to row 2, beryllium to boron, we would see an actual decrease instead of an increase in first ionization. And then we would see the same thing happen from nitrogen to oxygen. Okay, so we want to make sure we're aware of those exceptions to first ionization energy trend. Okay, now the reason why it happens between beryllium and boron and magnesium and aluminum is because we're talking about removing an s electron versus removing a p electron first. So the first electron being removed from aluminum would be from its 3p sublevel, whereas magnesium's a 2s sublevel. And if you remember off-bell diagrams, those vertical orbital diagrams, the p in the same energy level, the p orbitals are slightly more energy than the s orbitals. All right, so aluminum has one more proton in the nucleus, but that one more proton in the nucleus isn't strong enough to overcome the difference between a p orbital and an s orbital, right? So it's actually takes a little less energy for aluminum than magnesium. All right. And the same thing's true for beryllium to boron, just in energy level 2 versus energy level 3. All right. But for nitrogen to oxygen or the phosphorus to sulfur, remember, nitrogen is going to be up, 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 all unpaired electrons, whereas oxygen is going to be up, 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 down. So one of oxygen's orbitals is paired with electrons. When orbitals are paired with electrons, you get some electron-electron repulsion within the orbital, and that one more proton that oxygen has isn't enough to overcome those extra electron-electron repulsions within its 2p orbital. So it's actually a little bit easier to remove oxygen's first electron than nitrogen. Same thing happens with sulfur, okay? But then when we gain 2 more electrons, it goes back to trend, right? Okay? So understanding those exceptions is pretty important. Then, when you also look at ionization energy, you want to look at successive or subsequent ionizations. So you got first ionization, second, third, fourth, fifth, sixth, seventh, and it always gets more difficult. So second ionization energy is always higher than first, and third's always higher than second, and so on. It always gets more difficult to remove electrons, more energy required to remove them. Okay, but if you're given successive ionizations along a period of the periodic table, so here we're looking at row 3, right? Oops. What you want to look for is the big jump, right? So notice, like, sodium has the lowest first ionization, which it should because it's furthest to the left. And then, but if you look at magnesium's second ionization compared to sodium's second ionization, sodium's second ionization energy is actually higher than all of the second ionization energies of these elements in the third row. And that's because once you remove sodium's first electron, now any electrons being removed are now energy level 2 electrons, right? And so the big jump between successive ionizations tell you have how many valence electrons you have, right? And so it would tell you what column you're in. So if my big jumps between first and second, like sodium, I know I'm in row 1 or group 1, column number 1, right? But if the big jumps between second and third, now I know I have 2 valence electrons, and so I'm in group 2. All right. So notice, like, magnesium's big jump is here, aluminum's big jump is here, silicon's big jump would be here, and so on, because it's the difference between 1 valence electron, 2 valence electrons, 3 valence electrons. So I know that these are my valence electrons. This must be a core electron, right? This is my valence electron. This must be a core electron. These are my valence electrons. This must be a core electron, right? So that's kind of something else to watch out for in terms of ionization energy. Okay. All right, so it's probably good to just memorize your diatomic dot structures. All the halogens look exactly the same as fluorine, just they would be bigger because as you go down, radius gets bigger, so bonds would be longer and that kind of thing. But all single bonds with 3 unshared pairs around it, right? But I think the important thing is, like, remembering that O2 is a double bond and that N2 is a triple bond, okay? States of matter in terms of the halogens, iodine's a solid, but, bromine's a liquid, chlorine's a gas. They're all nonpolar molecules. It's just, iodine has way more electrons, so way bigger electron cloud, more polarizable, which means stronger London dispersion forces, right? And then fluorine would have weaker London dispersion forces because it has the least number of electrons, the smallest electron cloud of them, all right? All right, looking at bonds, which bond is polar? Well, you want to know that single bonds are weaker than double bonds are weaker than triple bonds, but then also there's bond polarity. The more polar the bond, the stronger the bond is, right? So why is the HF bond stronger than the HC bond? Well, this is a polar bond, a very polar bond, big electronegativity difference. You can call this a polar bond, but remember, we like to call this a nonpolar bond. It's a very small electronegativity difference, so you can call this nonpolar. But the other reason why this would be stronger is not just because of the electronegativity difference and making it more polar. It's also because fluorine has a smaller radius than carbon, because we know our trend. So this bond length would actually be shorter, and the shorter the bond, the stronger the bond, right? Hydrogen has a pretty strong bond, not because it's a single bond, not because it's polar, but because hydrogen is really small, so this bond is really short, okay? But remember, when comparing ionic bonds, you don't want to invoke electronegativity. Don't talk electronegativity. You can talk about difference in polarity, difference in dipole-dipole interactions, difference in bond polarity, difference in IMF strength, that kind of thing. That's electronegativity. When you talk about ionic, remember, ionic means there's already been the transfer of electrons. The electrons have already been transferred, okay? So now electronegativity difference doesn't mean anything, because instead of an unequal sharing of electrons like we worry about in polar bonds and electronegativity difference, one element's lost the electrons and one element's gained the electrons. So the transfer has happened. So remember, when you're looking at strength in ionic bonds, you're talking about you're just talking Coulomb's law, all right? Don't talk about electronegativity. It's not because fluorine's more electronegative than chloride. It's because fluoride is smaller than chloride. So sodium and fluoride are going to be closer to each other versus sodium and chloride. So that's going to have a stronger Coulombic attraction, okay? So remember, for ions, you're looking at size. Smaller would mean stronger because they can get closer to each other. But then also you're looking at magnitude of charge. That's the other thing in Coulomb's law, right? So if I was looking at magnesium fluoride versus sodium fluoride, magnesium slightly smaller than fluoride, magnesium slightly smaller than sodium, but also magnesium's 2+, whereas sodium's only 1+, right? So just thinking in terms of ionic compounds. Really just want to focus on Coulomb's law, okay? So dot structures for molecules, you kind of want to remember this, especially for multiple choice questions, right? Nitrogen, phosphorus, arsenic with 3 things where those 3 things could be a halogen or hydrogen, and it could be any combination of those. As long as those 3 things are halogens or hydrogen, right, that's where you get the trigonal pyramidal shape. It looks like this. If you're asked for bond angle, it's 109. Really, remember, it's 107 because the lone pair takes up a little bit more space than a bonding pair. But whenever you have 4 domains, you can, if you're asked for bond angle, you could say 109. And then whenever you have 4 domains, the hybridization is sp3, okay? If we look at oxygen with 2 things, sulfur with 2 things, selenium with 2 things, again, where those 2 things are hydrogens and halogens, that's where you're going to get your bench shape, right? Still 4 domains, so you could say 109, just like we set up here for trigonal pyramidal, but really it would be 105 because you have 2 lone pairs instead of 1 lone pair and 3 bonds. You have 2 lone pairs and 2 bonds, so the bond angle is actually a little bit shorter, but the hybridization is still going to be the same, sp3. And then when you have carbon with 4 things or silicon with 4 things, again, those 4 things have to be, halogens or hydrogens. That's when you get tetrahedral. It looks like this. That's when you get 109 degrees. And again, 4 domains always means sp3. Then remember, boron's good with 6 valence electrons. It doesn't have to have 8. So boron with 3 things is a common one that shows up with trigonal planar geometry. 3 domains means 120, and 3 domains around the central atom means sp2 hybridized. Okay. Silicon with 2 oxygens, carbon with 2 oxygens, carbon with 2 sulfurs, carbon with 1 oxygen, 1 sulfur. Okay, that's kind of right our quick linear molecule. Looks like that. 180, 2 domains around the central atom, sp hybridized. Okay. Remember, we have a thing called resonance. So like if I were to draw the dot structure for SO2, I would end up in a situation where I could draw the double bond here, but I could also draw the double bond here. So that's when you have to include your resonance structures. So you put both the structures in brackets and then you just kind of connect them with a double arrow. This would be 3 total domains. So it would be sp2 hybridized, 3 domains. So the bond angle is around 120. Now you could say 118 because you have a lone pair there. Okay. But instead of a bond, but remember 3 domains, you can always just say 120 for the bond angle. And again, I have my my resonance structures. Okay. So when you're drawing your dot structures, remember your must-have eights. That's going to be kind of important when you're filling in the blank of maybe an organic structure, knowing that oxygen needs eight. So if it doesn't have eight and it's not drawn in the structure, maybe there's some lone pairs that need to be around it, that kind of thing. But these are the must-have eights. So when you draw your dot structure, make sure carbon has eight, nitrogen has eight, oxygen has eight, fluorine has eight. Remember, hydrogen's good with two, so don't draw a bunch of lone pairs around the hydrogen, right? Hydrogen is just going to have a single bond to something, and that's it. Remember, boron's good. It says good with three bonds, good with a total of 6 electrons, not 8. It can have 8, but a lot of times you'll see boron with just 6. And then just remember, everything in row 3, so if we go to our periodic table, energy level 3, so silicon here and then down, they need to have at least 8, but they can have an expanded octet. They can have more than 8 because, remember, they have the empty d orbitals that they can expand into. And that's when you start to get the hybridization where you got sp3d or sp3d2 because you're hybridizing into the d orbitals, okay? All right. When drawing your dot structure, you only have to worry about formal charge if they ask you about formal charge. And a lot of times, most of the time, what they'll do with formal charge is they will give you 2 structures and say, you know, why is this one better than that one? And then you would calculate your formal charges. And remember, the rule for formal charge is if you can have a structure that has all zeros, then that's the best structure. Okay, but then if you have to have any formal charge, make sure the negative formal charge is on the more electronegative element of the structure. So here, this isn't, you know, if we were drawing our dot structure for CO2 and we were just following our normal rules for drawing dot structures, we could end up with this molecule. And if I asked you to draw the dot structure for CO2 and you drew that, I'd give you full credit, except if you drew it this way, you'd have to show the resonance, right? But the reason why this structure is not as good as this structure is because if we calculate a formal charge, in this structure, both oxygens have a formal charge of 0 and carbon has a formal charge of 0. But in this structure, one of the oxygens is a -1, but the other oxygen is a +1. And you don't want a positive formal charge on something that's more electronegative, okay? So that's why this structure is better. Remember, formal charge is number of valence electron the atom normally has minus 1/2 of the bonding electrons minus all of the unshared pair electrons that are around it. So like, how did I get +1 for this oxygen? Well, oxygen comes in with 6 valence electrons, 6 minus 3 bonds here. So 6 minus 3, okay, is 3. And then minus these 2 on the lone pair. So 6 minus 3 minus 2 is +1. Carbon comes in with 4. It has 4 bonds to it. So 4 minus 4, okay, 0. Okay, this oxygen, again, oxygen comes in with 6, -1 for the bond, minus 6 for these unshared pairs. So 6 minus 1 minus 6 is -1. Okay, so just, you know, watch out for a formal charge type question. In organic structures, carbon's going to follow, you know, one of these models, right? Carbon's got to have 4 electrons, but it's not going to have an unshared pair. So it's either going to have, you know, 4 single bonds, it's going to have a double bond and 2 single bonds, 2 double bonds, or a triple bond and a single bond, right? Here, if this carbon and this carbon in any organic compound, if this is the structure around my carbon, it's sp in linear, it's sp hybridized in linear. If it has 4 total bonds here, sp3 and tetrahedral. If it has 3 bonding domains, sp2 and trigonal planar. Okay. The one exception that you'll have carbon with unshared pair is in carbon monoxide. That's not organic, okay, because it doesn't have any hydrogen, but this would be an exception where carbon has a lone pair. But notice it still is satisfying its must-have 8 rule, okay? All right. So, like, here's an organic structure. What are they going to ask about it? They're going to ask, you know, is it polar or nonpolar? Well, whenever you have a functional group, you know it's polar. What's its strongest IMF? Well, it has an OH group, so you know it can have hydrogen bonding. Remember, everything has London dispersion, but we could say hydrogen bonding here. Okay, what's the shape and hybridization around this carbon? 4 bonds, zero lone pairs, so sp3 hybridized tetrahedral, sp3 hybridized tetrahedral. But here's where we have to remember oxygen is one of our must-have eights. I don't know what I just did. Uh-oh, I'm highlighting something. Hold on, let me pause. I'll come back. Okay, I'm back. All right. So this oxygen is not linear and it's not sp. You have to remember oxygen must have eight. So what's not drawn here? Two lone pairs. And there's two lone pairs on this oxygen. And a lot of times we would draw a lone pair here and a lone pair here. But that bond angle is still not 180, even though we drew it that way. You would have to recognize that this oxygen actually has four domains around it, two unshared pairs and two bonds. And that makes it sp3 hybridized. And this bond angle is going to be close to 109. Okay, so just watch out for that, right? So this is really what's going on. And still, this is a horrible representation, but a lot of times they draw it this way, and that's not a 180-degree bond angle. So be careful with that, all right? So here, here's an example. They gave this question maybe on last year's exam or the year before, and they like to do this. They, instead of just blindly drawing a dot structure of a molecule, they kind of have the molecules spaced out where they're supposed to be within the structure, and then you just have to kind of fill in all the bonds and all the unshared pairs. Okay, so like if you look at this, if you have to draw a dot structure given this scenario, right? You want to add up all the electrons, okay? And remember, so each carbon's bringing in 4 valence electron, each oxygen's bringing in 6, each hydrogen's bringing up 1. So that adds up to 24 dots. So you need to make sure you have 24 electrons representing the structure. So the first thing to do is just draw single bonds between everything, because they have to at least have single bonds to each other, right? So we'd fill in the bonds. So if we count the dots we have here, 2, 4, 6, 8, 10, 12, 14. But again, we need 24. So we need 10 more dots. We need 10 more dots. So that means 5 lone pairs. Well, where do you think those 5 lone pairs would go? Well, 2 of them would go here and 3 of them would go here to make sure oxygen has 8, right? So we draw, so now we have the right number of dots, but what's the problem? Carbon needs 8, but it only has 6 right now. So that's where you would take one of the lone pairs and put it here. And so this would be the correct structure. Okay? Now, if you weren't told to make sure you have the best formal charge, then the other way you could have done that was you could have put the double bond here. But if you memorize that this is what a carboxylic acid functional group looks like, right? The OH has the 2 lone pairs, and the O by itself has a double bond to carbon. That's a carboxylic acid functional group. Then you would know to just go right into the structure and just boom, 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 draw all your dots, and you're good to go. All right. But let's understand. Let's think about it. What would this bond angle be? A lot of people would make the mistake and call that bond angle there 180. No, 3 domains. It's 120. What's this bond angle? A lot of people would make that mistake and say 180. No, 4 domains. So that bond angle there is 109. All right. So just kind of like watch out for that. What's the hybridization of the carbon? This carbon's sp2. This oxygen, 4 domains, is sp3. This oxygen, 3 domains, is sp2. This carbon right here is tetrahedral shaped and it's sp3. Okay, so be able to kind of answer those questions. Okay. Here's just another example of resonance. But remember, when you draw a dot structure for an ion, make sure you put the charge in your structure as well. But, here is our example of resonance. Now, remember, what does resonance mean? Resonance means that this molecule doesn't have 1 double bond and 2 single bonds. It means all these bonds are identical, and the bonding is actually a weighted average of these structures. So the carbon-oxygen bond in this compound has 2/3 the characteristics of a regular carbon-oxygen single bond, and 1/3 the characteristic of a carbon-oxygen double bond. So characteristic in terms of length. So the length of these carbon-oxygen bonds are not as long as a normal carbon-oxygen single bond, but not as short as a normal carbon-oxygen double bond. It's a weighted average of all the bonding in the structure. Okay? All right. So the other thing you have to be able to do is tell if a molecule is polar or nonpolar. So remember, if you have a lone pair on your central atom, you're polar. If the ligands are different, you're polar. So like if I change this over here to chlorine, but these were still fluorine, that would be a polar molecule. This molecule is polar because it's asymmetrical. This molecule is nonpolar because it is symmetrical. Both the molecules have polar bonds. Okay, these bonds in this molecule are more polar than these bonds because there's a bigger electronegativity difference between fluorine and bromine compared to nitrogen and fluorine, right? Or not bromine, boron. But because this is a symmetrical molecule, it's nonpolar. There is no negative dipole and a positive dipole. You have a negative pole here, a negative pole here, a negative pole. Remember, to be polar, you have to have opposite poles. All right. So how do you know where the pole goes? The positive pole goes on the less electronegative element. The negative pole goes on the more electronegative element. So be careful here. A lot of kids want to put a negative pole here because there's a lone pair. That's not why there's a negative pole. A negative pole is on, or sorry, a negative pole is just on the more electronegative element because the more electronegative element is able to pull on those electrons. So here in this trigonal pyramidal geometry, the chlorines are pulling the electrons closer to down here and further away from the top of the phosphorus. So the top of the phosphorus gets the positive charge, and then the bottom of the molecules over here is the negative pole. So here's the positive pole, here's the negative pole. Here's the positive dipole, here's the negative dipole, right? And then if we drew another PCl3 molecule over here, then we would have, and then we connected with a few dots, the negative dipole of this molecule to the positive dipole of that molecule. That would be a dipole-dipole interaction, right? Okay. So that's part 2. We'll come back with part 3 here in a second.